Welcome to The Explainer. Today, I'm putting on my senior staff engineer hat to break down the highly structured, reliable design patterns you absolutely need to build production-grade agent harnesses. We're officially moving way beyond basic AI scripts today, and we're diving into true, robust architectural design. Here is our architectural review roadmap for today. We're going to cover frameworks versus agent harnesses, agent control and execution, data persistence, dynamic system prompt assembly, and finally, hooks, permissions, and safety.
All right, let's jump right into section 1, frameworks versus agent harnesses.
To start things off, we've got to resolve a massive point of confusion in the industry right now regarding the tools we actually use during the design phase. Frameworks. Think things like LangChain or AutoGen. They provide abstractions. They give you chains, memory components, retrievers, all basically as Lego bricks for humans to assemble. But a harness design pattern, that is fundamentally different. A harness is a fixed architecture built for the agent itself to immediately execute a task. There's literally no assembly step for you. It ships as a working, fully wired agent out of the box.
I love this analogy because it really hits the nail on the head. Think of the AI model as just the engine. Models are basically one-shot text generators, right? You ask a question, they answer, they stop. But the harness gives them the wheels to take action, see the consequences of those actions in the real world, and actually drive forward until the problem is completely solved. Now, to really understand this, we're going to break down the 9 core components of a harness. But instead of just throwing 9 random concepts at you, let's logically categorize them into 3 structural pillars. Pillar 1 is agent control, and that handles the execution using a while loop, tools, built-in primitives, and subagents. Pillar 2 is data persistence, which is all about managing your context and session memory. And Pillar 3 is safety and configuration, utilizing prompts, hooks, and strict permissions to keep the whole thing secure.
Which brings us nicely to Section 2, agent control and execution. Let's look at that first pillar. What is the actual execution engine controlling the agent's behavior? Well, at its absolute core, a harness is really just a continuous while loop engine paired with a tool registry. It's an incredibly simple step-by-step process. Step 1, the model reads its instructions. Step 2, it decides what tool to use. Step 3, it runs that tool. And Step 4, it feeds the results back in and just loops again. It keeps looping until the task is complete or, until it hits a safety iteration cap.
But an agent is really only as good as the tools it can access. To prevent the agent loop from just failing right out of the gate, we have to equip it with non-negotiable built-in primitives. Think about it. A coding agent isn't much of an agent if it literally can't read or edit a file, right? We also add specific workflow skills like git commits or running tests. And for those massively complex parallel jobs, that's where we spin up isolated subagents with restricted toolsets to divide and conquer the workload. Okay, moving on to Section 3, data persistence and memory.
Now that our agent can execute actions, we really have to talk about statecraft and durability. Because every single time that while loop turns, your conversation tree grows. And if you don't properly implement context compaction, well, you're going to hit the model's token limit. Yes, even those massive 1 million token limits. And when you hit that limit, your entire execution loop crashes. Compaction is absolutely crucial because it ensures your recent messages stay verbatim, while the older history gets elegantly summarized.
And for actually storing that session memory, honestly, keep it beautifully simple. Use append-only JSON files. Every single message or tool results gets exactly 1 line. It's brilliant because it flushes to disk immediately. So if your harness process suddenly dies for some reason, the memory file survives perfectly intact. It sits completely independent from the harness itself, which means you get flawless, seamless session replay.
Next up is Section 4, dynamic system prompt assembly. Now, diving into our configuration layer, this is a component that honestly surprises a lot of developers when they migrate over from standard LLM apps. In a basic app, your system prompt is just a fixed string, right? But in a production harness, the system prompt is a dynamic assembly pipeline. At runtime, the harness literally walks your project directories, hunts for specific files like an agents.md, and injects those precise workflow instructions directly into the agent's brain on the fly. But, and this is a massive warning straight from the architectural trenches, you have to be incredibly careful with how you design this prompt assembly. If you mess up the order of dynamic injection, you will completely break strict prompt caching. You absolutely must assemble the static, unchanging parts of your prompt first. If you inject dynamic content at the very top of the prompt, you're going to invalidate the cache on every single turn. That is going to totally spike your latency and send your compute costs through the roof.
Finally, we've reached Section 5, Hooks, Permissions, and Safety.
This is the climax of our design review, because these strict safety layers are exactly what separate a highly useful harness from a dangerous liability. To make your harness truly enterprise-ready, you have to implement lifecycle hooks. They give you seamless extensibility and observability, all without ever touching that core execution engine. Pre-tool hooks fire before execution, giving you the power to intercept, allow, or deny a tool call. Post-tool hooks, on the other hand, run strictly after the execution to provide a rock-solid, unalterable audit log. But safety isn't just about logging after the fact, right? It's about strict, violent enforcement of access control. Every single tool in your registry has to declare its minimum required permission tier at dispatch time. We're talking a clear hierarchy here. A tool might need read-only access just to list files, workspace-level access to edit your code, or full access to execute highly destructive system tools. And this is exactly why dynamic command classification is so vital. Let's walk through this workflow. Step 1. If an agent tries to run a bash command, the harness has to dynamically parse that string. Step 2, it classifies it. If it's just concatenating strings or grepping, it stays safe and read-only. But step 3, if the harness catches a dangerous command that requires full access, like a delete or a sudo, it must immediately pause the execution loop. It stops everything and triggers an interactive human approval hook, forcing it to ask you for explicit permission before it proceeds. Ultimately, true autonomy isn't just about the intelligence of the AI engine. It's about the durability, the safety, and the fixed architecture of the car you've constructed around it to let it drive. So as you go back and look at your own architectural deployments, I want to leave you with this final thought. Is your agent really limited by its model, or is it limited by the harness you built for it? Thanks for joining this explainer. See you next time.